Good afternoon, everyone. My name is Caitian. I'm a research fellow in NTU. Today, I'm very glad to attend this conference. So my talk is about engineering the electrochemical temperature coefficient for efficient low-grade heat harvesting. I will give my talk following these four parts. First is about thermal energy harvesting, and then I will give an introduce about TREC. Then it's about my research for engineering temperature coefficient for the efficient TREC system. And finally, I will give a conclusion as a perspective. So as we know, the heat is very abundant in our environment, like solar heat, geothermal, industry heat. Normally, this heat are lower than 100 degrees Celsius. It is so-called low-grade heat, and it has several disadvantages, like it is very abundant and promising for the energy supply, especially for the large grid-scale applications. But it still have a challenge to apply this low-grade heat because normally it distributes in a very large scale and the temperature differential is very narrow. Actually, there are several technologies try to harvest this kind of low-grade heat. Firstly, I want to introduce the solid-state thermoelectric device. It is a traditional TE device. It's based on Seebeck effect. Normally, the ZT figure merit is lower than 1.5 for the low-grade heat harvesting. So the efficiency is not that good. And also the material is quite expensive. The second technology is a Thermogenic Cell. This cell is in the electrochemical system. Normally, in the electrochemical system, the redox reaction also has such similar Seebeck effect. Such ferrocyanide pairs, the temperature coefficient for this pair is larger than 1 milliwatt per Kelvin. But due to the large resistance and bad ionic conductivity in the electrochemical system, the power conversion efficiency is still lower than 1%. So today I want to introduce a new technology, thermally regenerative electrochemical cycle, TREC. Before this, let's see our daily used how our daily used battery works. Normally, we charge our battery at higher voltage and discharge our battery at lower voltage. That means we have some energy loss during the charging and discharging process. And the battery is the electrochemical system. From the Gibbs free energy equation, we can know the potential is related with the temperature. That means from some extent, we can tune the potential from by the temperature. And then maybe we can flip the discharging curve and charging curve. Shift the discharging curve upper than the charging curve. That means we can overcome the energy loss and gain additional energy from the temperature. This is the main idea of the TREC system. Normally, the TREC cycle contains 4 steps: heating, charging, cooling, and discharging. If we draw such steps using the voltage time curve, we can have such curve here. So during heat, if the cell has a negative alpha, the potential will decrease. Then we charging the cell to some higher voltage. Then we cooling down the cell, and the potential will increase with the temperature decrease. Finally, we discharge our cell at higher potential to the original state. If we draw a loop curve here, we can see the discharging potential is larger than the charging potential. That means we overcome the energy loss and get some additional energy from the temperature. In this study, the electricity conversion efficiency is up to 5.7%, and it equals 38 Carnot efficiency. So in the TREC system, the electrochemical temperature coefficient alpha is a key factor. So this factor decides the efficiency, also decide how we can run the TREC system. And as we know, the materials determine the performance. So one of my study is focused on design the materials and study how the materials affect the alpha value. One of the materials I studied is Prussian blue analogs. This material normally is a good electron material for the electrochemical system, and it is very environmental friendly and also very low cost and very quite stable. And also this material has a quite large family, depends on different transition metal M1 and M2. So my curiosity is how this elemental change affect the alpha value. So I synthesized different PBA materials here, like cobalt copper PBA, cobalt green PBA, and copper PBA and nickel PBA. We can see these materials have distinct color. And we do the TM analysis, we can see these materials all have the cubical structure. From XRD analysis, the material has high crystallinity and belongs to the cubical structure. And from also we study the morphology. And normally this kind of material has around 100 meters size. Then I study the temperature coefficient in these materials. This is a test of our alpha value. So we switch the temperature in the cell and record the potential potential of the cell. And from here we can see when the temperature increase, the potential is decreased. That means our cell, my material is like have negative alpha. So in these three materials, it has different alpha values. Cobalt copper delivers the largest alpha value around minus 0.89 milliwatt per Kelvin. And we also studied this material, cobalt green PBA, and we found a very interesting phenomenon. At the higher reaction plateau, this material delivers negative alpha value, about minus 0.38 milliwatt Kelvin. At the lower reaction plateau, this material has a positive alpha value around 0.43 milliwatt per Kelvin. So the question is, why different materials have different alpha value, as some materials even have the alpha, the sign change in the materials. So from the equation here, we can know the alpha is decided by the entropy change during the electrochemical reaction. And in this study, what I did is we changed the metal type. Yes, cobalt, copper, nickel. That this one may affected this term, the phono vibration entropy in the electrochemical reaction. So we try use the XC2 XRD to study the electrochemical process. And from the analysis, we can see all these three materials has a negative alpha, and during the cation intercollection, these materials all have the lattice shrinkage tendency, and the shrinkage ratio are different. In this material, cobalt green, we found initially it has a lattice decrease tendency, and then the lattice increase. That means cubic shrink initially, and then with the intercalation of sodium, it expansion again. So it's very interesting. And we draw such plot here, and we found these three materials, the lattice parameter decreased during the sodium ion insertion. And that means the lattice has a shrinkage tendency. And that means the phono vibration entropy decrease. our materials have the negative alpha. But in these materials, initially, the lattice has a shrinkage tendency, and it delivers a negative alpha. But with more sodium ion insertion, the lattice parameter increase, and that means the structure expansion, and it delivers a positive alpha. So this theory can explain our result very well. Also, we performed the DFT simulation here, and we studied the lattice parameter change in these materials, and also the phono vibration entropy values are here. This kind of theoretical simulation consisted with our experiment data very well. So as the study in here, we found copper has a very large temperature coefficient. So we apply this material in our TREC system. We run a TREC cycle between 50 degrees Celsius and 10 degrees Celsius. We can find our discharge curve is larger than charge curves, and we have about 3.67% energy conversion efficiency. It equals 28% Carnot efficiency. To point out here, this is just half cell. We may gain higher efficiency in the full cell. Also, we studied the stability of the system, and we found it quite stable after 50 cycles. So here I want to do a brief conclusion here. So in this study, I try to engineer the alpha value in various PBN materials, and I discover very large alpha value in the cobalt green, cobalt purple material, and also this kind of alpha value is related with lattice parameter change, which determines the phono vibration entropy. Also, we run the TREC, use these materials, and get a promising efficiency value in this temperature range. So the TREC system actually is just new developed. There are still many unexplained phenomena, and also we should try to study more materials with positive alpha and even larger alpha value. Also, this system should be optimized to, I mean, the structure of the system should be optimized to gain more improved efficiency. Also, we should apply this system to more practical applications. Finally, I want to thank my professor, Li Suku. He supported me a lot during my postdoc period. Also, I want to thank my group members, and because of them, I have very pleasant time in Singapore. And also the funding agencies, MOE at A-STAR. Also, I greatly appreciate this chance, and thanks for the organizers. Thank you.